Hello, and welcome to the start of Unit 7. So, Unit 7 is about rational functions. So, we're going to be taking a look in this lesson, 7.1, about the parent rational function. You can actually see that right there. It's talking about 1 over x and its transformations. So, if I shift it up and down, left and right, we're going to talk about asymptotes and end behavior and just things like that. As well as talking about just introducing general form of a rational function, which we write two polynomials being divided. And I'll say more about that later. But that's kind of the premise of this video. All of Unit 7 is about rational functions, but there's various topics that we're going to go through. These first three lessons, from point 1 to point 3, these are going to be about graphing rational functions, okay? So what do the graphs of these things look like? And so we're going to see what the parent function looks like here, and then we'll move on to transformations, and that will really be all we do in this video. But other videos will cover much more in depth what to do with any rational function, maybe ones that don't look like the parent. So yeah, let's get started here. I'm going to say key. Let's go ahead and start. So we're going to graph the parent function to start with, and this doesn't take a whole lot of time, but I am going to explain all of its features. If you already know the parent function, you can skip ahead of this if you already know this, right? But I really just want to take this minute to talk about why these features are here. Like, it's not just a shape for the sake of it. There's a reason we have... There's a reason it looks the way it looks, and so we're going to look at that, okay? So the first thing I got here is we're just going to fill out this little table here, plugging those values into the function y equals 1 over x, yeah? So say, well, what happens? I mean, you could call it f of x, right? So we're evaluating all of these. So I say, what's f of negative 4? Well, if it's f of x is 1 over x, then this is 1 over negative 4. So, I mean, that's just negative 1/4, right? And we're just going to keep plugging those values in. I don't really need to write all that. 1 over 3, I mean, negative 1/3, if I put negative 3, then negative 1/2, and then negative 1, because I have 1 over negative 1 gets me negative 1. And I can try to draw some of these points, right? I've got some fractions here. So at negative 4, it's about 1/4, maybe about right there. Then about 1/3 at 3. I don't know, that looks more like half. I'm not going to be too picky here, but, you know, I'm going to try. Oh, no. It still looks like half. That should be halfway. Maybe there's 1/3. Okay, that's a little bit better. And then negative 1. Don't worry, you don't need to be this picky with your graph, okay? I'm just trying to get a nice, accurate curve so you can really see those dots. And that's that side, right? And I'll continue plugging in points. And the next one I got is 0. So I say y equals 1 over 0. And I say, oh. I say, what is this? Oh, I meant to raise the eyebrow on that. I say, what is that? Well, 1 over 0 is what we call undefined, right? I can't divide by 0. We don't have a definition for it mathematically, right? So division by 0 doesn't exist, right? And it's not like the same sense of an imaginary number, quote unquote, not existing, but like there's just nothing, right? There's nothing we can do, not in Algebra 2 at least. Maybe higher math, maybe there's some field of math where we can allow ourselves to divide by 0, but not right now, not with the rational function. So okay, we'll just kind of skip that one. Say, I don't think it exists there. And so we'll go on to 1. I say 1 over 1 is 1, then 1/2, 1/3, and 1/4. And so I'm going to draw some of those points. Maybe not be as picky here. I got 1, 1, and then 1/2, and then 1/3, and then 1/4, right? And so I've kind of got that going on here. And you might say, well, what is this graph going to look like? I mean, is it coming around like this, and then going to kind of come up and then over or something? And then just maybe there's just like something weird going on? I mean, what does this look like, right? So we're going to generate some more points. It would help to know how is the graph behaving between -1 and 1? What is going on in this region, right? So I say, well, let's continue our table. Say here's -1/2. So when I plug in -1/2, that's 1 over -1/2, and 1/2 goes into 1 twice. So -2 would be the result of that. So at -1/2, it's -2. At -1/3, it's -3. And you can kind of see that this is going to continue for all my fraction values here. I'm going to get closer and closer and closer there, right? And that's just going to keep on going. And similar idea, when I plug in 1/2, I get 2. 1/3, I get 3. 1/4, I get 4. And I'll plot some of those. 1/2 here, and then here, and then here, right? And so I'm kind of starting to see what this curve really looks like. And I can also imagine what's happening. I say, well, what is happening as I get close to some of these numbers? So let's see, let's put some space here. As x approaches, let's say what do we want to start with? Let's start with infinity. Let's just do that one. As I go to the right, what's happening here? Well, as I'm going to the right, these values are getting smaller and smaller and smaller. And you could probably assume, following this pattern, 1, 1/2, 1/3, 1/4, if I put in 100 here, I'd get 1 over 100. If I put in 1,000, I get 1 over 1,000. And you'll notice that these fractions get smaller and smaller and smaller. It appears that they're going somewhere, right? They're getting close to something, but they're not quite reaching it, right? I could say 1 over a really big 10-digit number or whatever, right? And I say that's not quite nothing. It's something there, and it's not negative, but it's really close to 0. As I say, okay, so this graph is going to kind of come on down towards 0. But it's never really going to touch it, right? It's never going to reach 0. So I put a little arrow here, and it's implied that I never rest on 0. I never touch it. So as x goes to infinity, f of x seems to be going to 0, right? The y values are going down to 0, but not any more than that. They're not going, oh, no, I didn't mean to delete the curve. There we go. Just the arrow. That's nice. And so I see that. If I do the same thing for the left side, if I go to -infinity, I will see the same thing. The function will also be going to 0, just kind of approaching it from the bottom here, right? So it's gonna come here, and then it's gonna smoothly wrap down like this, around a nice curve. There we go. It's kind of coming like that, right? Now, the thing is we're never reaching 0. So to really inform the reader, whoever's reading this graph, that it doesn't touch 0 or that it's getting close to 0, I'm going to use a dashed line. And this dashed line is, I hope you remember from Algebra 1, called an asymptote. And we'll see that word off to the side in just a second. But I have this dashed line. This is actually called a horizontal asymptote. It is a line that the function is approaching. And this line in particular is y equals 0. As I go to the infinities, I go to 0 in both directions. Both positive infinity and negative infinity goes to 0. And so that's my asymptote. I'm not going to write out the definition word for word, but really what an asymptote is if you have a function, an asymptote is a line such that the function values on this function curve, this thing I'm sort of drawing right now, the distance between that curve and the line decreases. So you can notice that this distance is getting smaller and smaller and smaller and smaller and smaller. And it's going to keep going like that. And so the distance between these two lines decreases forever, never really stops, right? So the distance keeps on going down. Cool. Now, what's happening in the other direction? I say, what's happening when you go to 0, right? Again, if you already know all this stuff, you can skip it. It's okay. But it's a good conversation as to why this function looks the way it does. As x goes to 0, well, you might say, well, from the left or from the right, right? Like, because it's kind of doing two different things. Do you mean from left to right like this? Or do you mean coming to 0 from this direction, right? Well, we actually have a way to specify that. I say as x approaches 0, and I'm going to put a little plus above it. And that plus means I'm coming from the positive. So from the positive side out here, I'm going to approach 0 this way. So it's from the right, right? Well, as I get closer and closer to 0, the y values seem to be increasing, right? And they're going to kind of keep on going up and up and up. And this makes sense because for the same reason, if I plug in a really big number, like, 1,000, 10,000, right? I get 1 over 10,000. If I plug in 1 over 10,000, then I'm going to get 10,000. And so that's going to be a really tall value. So I'll be really close to 0, but it sort of reaches up and up and up. And so that is going to reach towards positive infinity. Let's just say, so f of x goes to positive infinity. If I do the left side, you can see it's going to be the opposite nature. It's going to go down and down and down. It's going to reach towards negative infinity. So f of x will approach negative infinity. Okay? And I put a little negative because it's coming from the left. You'll see that notation a lot in calculus and pre-cal. So I'm going to put another dashed line because vertically I'm getting as I'm sort of approaching 0, but I'm not quite reaching it or crossing it, right? I'm just getting close to this value 0. And so that is a vertical asymptote at x equals 0. And this image is the rational parent function. Know it well. You're going to want to know what this image looks like, but also why this exists, right? I mean, there's a reason I spent so much time talking about this. Where are these asymptotes coming from, Because we're analyzing the behavior of the graph around certain points. We're looking at the behavior of the graph at 0. We're also looking at the behavior of the graph at infinities. And, that seems simple enough, but that's really the major focus of when you study these functions. We're going to have various asymptotes, ones that are horizontal, ones that are vertical, and there's going to be particular values we're interested at looking around. But more on that later. For now, let's fill out the rest of this so we can move on, because Mr. Spake has been talking way too much about this parent function. X-intercept, well, I don't see any. There's none. Y-intercept, I don't see any. There's none. So there are no X or Y-intercepts. I have asymptotes there. Asymptotes I am not touching. I don't like the way I'm drawing that in. There we go. There we go. That's better. Yeah. So I'm not touching that. Domain and range, we're going to use interval notation for this. And you should remember when we covered this in the first part of the year, we use a union symbol because these are two disjoint sets. If you think about a number line, the function is defined for all negative values up to here. It's also defined for all positive values. The only place it's not defined is 0, right? 0 is the only x value that we don't touch, right? That we don't cross, there's nothing there. And so it skips over that. Similarly, you can see the behavior in the y direction. All the negatives are included. All the positives are included, but not 0. We don't touch 0. So the range excludes 0. Notice I'm not using bracket because a bracket would mean inclusive. So we have strictly parentheses here. We do not touch 0. And there it is. Cool. All right, let's move on. So rational functions and standard form transformations. Now, this piece of the lesson was a little bit of exploratory. I'll go ahead and just sort of mimic the exploration here. But what students were supposed to do is type in this function into Desmos. So f of x equals a over x minus h plus k. And so I'll go to Desmos, and I'll type it, because why not? F of x is a over x minus h plus k. Say plus k. And I'll add a slider for this. And so you can see my function here. Let's set h and k to 0 because the function is centered at 0. So there's the parent function, right? That's who we just graphed. And we're just going to adjust these sliders. So what does a do? Well, as I move this slider back and forth, maybe let's do back and forth for positive values. You see a kind of dilation here, sort of stretch, right? So as a increases, we'll just call that a vertical stretch because the y values are being expanded, right? They're going up. It's getting taller, right? As I increase a. If I decrease a all the way towards negatives, right? Notice what happened. Think about what quadrants it was in. Before it was in quadrant 1 and 3, and then it flips. It switches to quadrant 2 and 4. Right? So it's switching quadrants. This is a reflection. You might say, what kind of reflection, right? Is it across horizontal? Is it the vertical, right? Well, the thing is it's either, because you could imagine you can imagine the curve that's currently on the right being flipped to the left. But you could also imagine, take the same image, take the curve on the right and flip it down. And so it's actually the same image. And the same was true for the other branch. So you can call it a vertical reflection or a horizontal reflection. Either is true. Don't call it both, though, because if you reflected it twice, you'd be back to where you were. Let's see what h does. So if I move h around, it seems to be moving the vertical asymptote, right? That is shifting, because usually it's at 0, but if I make h positive, if I subtract a positive number, it is, here's at 4, right? I can see that the vertical asymptote is 4. And I shift it left to the negatives, I can see that too. So that's the moving left and right. And of course, k is moving up and down. So k is affecting the range, it's affecting your y values, right? In particular, the horizontal asymptote. Yeah, so it just moves it up and down. And that's it. That's really all that is really supposed to show you, okay? So you can say that h moves left and right, k moves up and down, and a, like a always does, is a vertical stretch and a vertical reflection. I'll just settle for vertical reflection. You can call it horizontal. I'll say horizontal reflection is valid too. Okay, because it does make the same image. And as we just noticed, the vertical asymptote is affected by that shift h. So when I said if I said 1 over x minus 2, then the vertical asymptote was 2. It shifted it right 2. And we've done function transformations before, so this isn't brand new, right? Y equals k shifted it up and down. So there it is. And that affects the horizontal asymptote. So I'm going to do a quick example here. It says graph the function 3 over x plus 1 plus 4 and identify, not identity. Oh no. I hate when I make typos. Identify. There it is. That's a little bit better. Its key characteristics. So, as we just noticed, a is 3, so it's being stretched by 3, vertical stretch by 3. H it's a shift left 1, so it's negative 1, because I'm doing subtraction by negative 1 to get plus 1, so that's left 1. And k is up 4. And so h and k actually tell me where the asymptotes are. The vertical asymptote is shifted left 1, so it's at x equals negative 1. The horizontal asymptote is shifted up 4, so it's y equals 4. And so I'm going to graph that, right? So negative 1, I'll draw a dashed line for my asymptotes. By the way, it's very important you have these. Very, very important. Well, at least when it comes to grading. Yeah. I'm going to be looking for these dotted lines. Being meticulous about it. And so I've got those. And now I say, okay, how do I find these other features, x and y intercepts? Well, we know how to find an x-intercept, right? To find an x-intercept, maybe I'll do this in blue to kind of make sure this isn't overbearing. X-intercept. To do so, you set f of x equal to 0 and solve. This is always how we find x-intercepts. If you remember, go back to last semester, f of x equals 0, the things that make that true are called roots or solutions or zeros, and that's x-intercept, right? So I'll set the function 3 over x plus 1 plus 4. I'll set that equal to 0. There's a multitude of ways to solve this, but I'll first subtract 4 to get negative 4 over here. Now, I like to flip my proportions. I don't know if a lot of people do that. So a lot of people instinctually will multiply by x plus 1 on both sides, and that's fine. So I guess I'll do that. Mr. Spake would like to say that it's x plus 1 over 3 equals negative 1/4, because it makes it maybe just a little, I don't have to distribute as much, but whatever. I'm going to multiply by x plus 1 on both sides. This is the standard way. I don't care. Whatever. Who cares? Pick whatever works. And so I got this, right? Now, you can divide by negative 4, or you can distribute the negative 4. Okay, you know what? I'm halfway doing this. I hate this. I hate this. This is how you do it in Algebra 1, and I don't like it. Because in Algebra 1, you distribute the negative 4, and you get negative 4x minus 4 equals 3. And then you add the 4, you get 7, you get negative 4x. This is too much work. Oh my gosh. You know what? I've changed my mind. Mid-video, Mr. Spake's changing the plan. I'm going with the proportion thing. I'm flipping it. I'm saying this is true. You say, Mr. Spake, you can't just do that. I say, yes, I can. That's my video. I say, look, 1 is to 2 as 2 is to 4. Yes? Then 2 is to 1 as 4 is to 2. No? Correct? Of course. You're allowed to do this with proportions. I'll then multiply by 3 on both sides, and I get x plus 1 equals negative 3/4, and then I'll subtract 1. I say negative 3/4 minus 1. If you need me to write that, I say x is negative 7/4. Nice. So that is the x-intercept. So I put this over here as negative 7/4, comma 0. Yay! Okay. See how I didn't have to do any unnecessary distribution? That's just silly. I just hate doing that. It's just no. There's many different ways to solve problems. You don't have to do it the same way every time. Okay, the y-intercept. How do we do that? Well, it's got some space over here. For the y-intercept, you just, you evaluate f of 0. That's how you do it. You plug in 0, right? So I say, okay, f of 0 is 3 over, it's x plus 1, but instead it's going to be 0 plus 1 plus 4. So that's 3 over 1 plus 4, which we know is 7. So the y-intercept is 0, 7. I'll switch back to red and plot these points. The y-intercept is at 0, 7. The x-intercept is at negative 7/4, 0. That's close to negative 2, so it's about right there. And that's it. Those are the intercepts I've got. And because of these points, I say, well, it's going to look like this, but it's going to kind of curve over like that. And so, unlike maybe the previous unit where I said, you really need to find pretty points, in this unit, for graphing, we're really just interested in the asymptotes, okay? If you can figure out where the curve is supposed to be and approach it correctly with the asymptote, that is just amazing. That's the goal, okay? So I'm going to kind of curve down here. Oh, I don't like that curve. I could do a better curve, I believe. So I'm going to kind of come up here and approach this asymptote like so. make it flat right there. Okay? This is a nice big point here, and then come on down like that. Cool. And that is sufficient. Okay? Again, graphing expectations here is that you plot those asymptotes with dashed lines. Do be sure to plot x and y intercepts. But aside from that, I don't need other points. It's okay. As long as it's in the right quadrant or whatever, it's right in the right region and approaches the correct asymptotes, you are fine. And then for domain and range, I'll see that I'm skipping both asymptotes. So the domain is not including the vertical asymptote, which is at -1, right? If you're reading it from left to right, yes, 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 yes. I'm defined, I'm a lovely function, and then, oh no, -1, and then yay, after, right? Same story going up. I don't like 4, so I'm skipping 4. 4 is not part of the range, okay? I'm approaching 4, I'm not including 4. And there it is. That's the example. And to be honest, I should stop the video there, but I won't. I'll keep going. Let us continue. So, rational functions in general form. So it says in lesson 7.2, we will learn how to analyze these attributes when given in general form. So just a quick word about that. What is general form? This is the way we usually write it. Okay, standard form, which is this, is useful for transformations, but they're usually not written that way. The reason they're called rational functions is because they are a ratio of polynomials. So given two polynomial functions, p and q, divide them. That's a rational function, okay? We can do this. We can go from standard form to general form by finding what's called a common denominator. Yay, fractions. Woohoo. So that's what we're going to do. Okay. So example. And we'll all the rest of the videos are about general form, okay? So we'll definitely hit more on it, but the idea is you're combining this into a single fraction, okay? In class, we did a warm-up about adding these fractions. Well, if you need a refresher on adding fractions, I think that's another video. But I will show you how to do this one, okay? Here we go. Fractions always give us trouble, right? We love fractions, but they're tricky. Say x plus 1 plus 4. Okay. So in order to add these quantities, you must have a common denominator, right? I mean, how do I add 1/2 plus 1/3? I say, well, I multiply this by 3/3 and this by 1/2. And then that way I get everything in terms of sixths, right? Well, the denominator here is x plus 1. So I'm going to write this as 4/1. Not necessary, but whatever, I will. Times, I need the denominator to be x plus 1. And I will use parentheses with this because distribution is going to be very important. So what does this become? Well, I get 3 over x plus 1 plus 4 times x plus 1 over x plus 1. Yeah? Now that 4 is going to distribute, and I'm going to get, well, whatever. You know what? Let me hold off on that. Then I'll say it's 3 plus 4 times x plus 1 over x plus 1. I combine these because they have the same denominator, x plus 1. Then I can distribute 3 plus 4x plus 4 over x plus 1, ending me with 4x plus 7 over x plus 1. And that is it. Yay! Okay. That's it. That's how you do that. Okay. It's just getting common denominator practice. It's just making sure your algebra skill is okay on that. We'll be doing a lot of this later in the unit. So like 7.4, 7.5, something like that. We're going to be finding much more complicated denominators. So this is just a sort of taste of that. And that's general form. So next lesson, we're going to see if I gave you this function, how would you have known that the vertical asymptote was -1 and that the horizontal was 4? right? How could you have told that from this equation? And so we'll be talking about that next time. Okay. At this point, it's student practice, so that's the lesson. You're not going to miss anything if you stop watching here. But if, maybe some of the fractions are giving you trouble, maybe some of the homework questions you need a little bit of help with, and maybe me doing these examples will help out. Yeah. So we're just going to do the same thing we just did. It's just more practice. Yeah. And I'm just going to talk about them. But I'll probably go through them a little bit faster. So this is more of a key than explanation. So the first thing is I'm just going to analyze transformations. A is 4, H is -2, and K is -3/2. Right? This means a stretch by 4, vertical stretch by 4, but honestly, I don't care what you say. Say vertical stretch. This is moving left 2 and down down 3/2. So my asymptote vertically is shifted left 2. So I'm going to put that here, like so, okay? And then it is down 3/2. So I got to eyeball this a little bit, but instead of being at 0, so that's 0, I'm going to be at -1.5, so about halfway in between these. And that's okay. These fractions are going to happen. It's cool. We're chilling. So my vertical asymptote is at -2. My horizontal asymptote is at y equals 3/2. I do want to note real quick that it's important you write the equation, not just -2. I'm not being lazy and just saying -2. I'm saying x equals -2. That's important. You need the equation. Let's find our x and y intercept. So to find an x-intercept, we set it equal to 0. So I say x-intercept. We're going to set 4 over x plus 2 minus 3/2 equal to 0. And we'll just solve this. So I'll add 3/2 to the other side. So I get this. And this is why I like those proportions. A lot of people like to cross multiply here. Like multiply this. We call that the butterfly method. Okay, if you want. It's your math. You can do that if you like. I'm not going to. I'm going to say x plus 2 over 4 equals 3/2. I'm flipping the ratios, flipping the proportions. Because if you took 7th grade math, you know you're allowed to do that. From here, I'll multiply both sides by 4, which gets me x plus 2 equals, 2 times 4 is 8, so it's 8/3. And then if I subtract 2, I should get x equals 2/3. Okay? Because it's 8/3 minus 6/3, and there it is. Yeah. If you want to pause the video and follow all that algebra, you're welcome to do so, yeah? And so I got 2/3 comma 0. That's about right here. Just eyeballing it. Let's do this in yellow now, y-intercept. My favorite one to find, I just look at f of 0. And so my function is 4 over 0 plus 2 minus 3/2. So that's just 4 over 2 is 2 minus 3 over 2. That's 2 minus 1.5, which is 0.5 or 1/2. So the y-intercept is at 0 comma 1/2. Let me stay consistent and write it like that, because why not? Alrighty. And so I'll come over here, 0 comma 1/2, about right there. Okay, that's sufficient. And so I'll say, all right, well, I got 2 points there, so they're going to kind of connect here and go up. So make those nice big bold points. Approach the vertical asymptote this way. And then approach the horizontal this way. Okay. Make that nice big point there. Okay. With the other curve, they're usually, with simple functions like this, they're going to point in opposite directions for the across the vertical asymptote. Sorry, I couldn't think for a second there. real-time thinking. Okay, I was drawing that. So, if this one points up, this one's going to point down. Don't take that as truth for all rational functions, because that's definitely not true. But for the simple ones today, it is. Okay. Our domain is not including -2, so we will skip over that. It's a set of all real numbers, not including -2. And the range is all real numbers, not including 3/2. And so I'm writing what I'm writing and saying it verbally. Lastly is finding the general form equation. So I guess I'll switch to, I'll just keep doing this in blue. It's not a big deal. So I've got 4 over x plus 2 minus 3/2. I need to get a common denominator here, right? And so this is probably the piece of the video you're watching if you're stuck on this. Let's say general form to indicate in the notes for you. So to find general form, you need a common denominator. So the way you do this is, this denominator is x plus 2, this denominator is 2. So this needs a 2, and this needs an x plus 2. Now they're the same. So I just multiply this one by x plus 2 over x plus 2. And I multiply the other one by 2 over 2. Okay? And I'll put parentheses around that. And so, okay, let's do that multiplication. 2 times 4 is 8 over 2 times x plus 2 minus 3 times x plus 2 over 2x plus 2. You could put this together over 1. You say 8 minus 3 times x plus 2 over, and I'll just go ahead and distribute 2x plus 4. Let's distribute the -3. So 8 minus 3x minus 6 over 2x plus 4. Fully simplified is 8 minus 6 is 2. So it's 2 minus 3x over 2x plus 4. I can leave it like that. That's fine. I'll go ahead and write it as -3x plus 2 over 2x minus plus 4. And that is good. I could also say, alternatively, you could write this as -3x minus 2 over 2x plus 4. That is equivalent and perhaps preferable, because that negative shows, I don't know what it shows. I guess it doesn't show anything. It's just a negative. Yeah, and there it is. Cool. All right, let's do another. I'm getting hungry. My fiance, soon-to-be wife, about a week away from now, my fiance just made spaghetti, and it's been sitting there for 20 minutes, and I need to go eat, but I'll finish this last problem here. Isn't it so nice for her to cook for me? It's so sweet of her. I love that woman. Okay, let's find all the same junk for this function. This one's a little bit tricky just because you want to factor the denominator first. 2 times x minus 3. You say, Mr. Spake, what? I said, well, you're just like supposed to, Like, like, why weren't you? No, that's just what we do with function transformations, right? Because these are really of the form a over b times x minus c plus d. So we factor that b value out so we can really see the shift to the right. So I'm not going to bother writing all the function transformations. It's exhausting. It's vertically reflected. It's horizontally stretched. It's shifted right 3 and up 2. Okay, there's your verbal description. So the vertical asymptote is at 3. You say, Mr. Spake, you're rushing. I say, I know, I'm kind of hungry now. So vertical asymptote is at +3. So I've got this, like so. And the horizontal is at 2. Beautiful. Let's find our x and y intercept. X-intercept, this is going to be a little annoying. I don't know, let's do yellow. X-intercept is going to be negative 1 over 2x plus 3 plus 2. We're going to set this equal to 0. Let's just add the fraction to the other side, yeah? There's 2 equal to 1 over 2 times x plus 3. A lot of times you guys will subtract 2, and then it's all the same, right? It's all the same. Let's flip those ratios. So 2 becomes a half, and 1 over that becomes 2 times x plus 3. We can divide by 2 now and get a fourth equals x plus 3. See, I said that's divided by 2, and that's divided by 2. You cut a half in half, you get a fourth. And so then I subtract 3, getting me 1/4 minus 3 equals x. I say therefore x is what is that? What's 1 minus 12? That doesn't seem right. Hold on, that doesn't seem right. Did I do this right? I feel like I did. I feel like that's not what I got in class, though. 1 minus 12? Negative 11/4? Eek. You know what? I'm going to graph this. Negative 1 over 2x minus 6. Oh, is it minus? Is that why? That's why. Silly goose. It's not plus. It's minus. You were probably screaming at the little laptop or phone or whatever you're watching this on. You're probably saying, Mr. Spake, it's minus, not plus. So 1/4 plus a third. There it is, 13/4. That's what I thought it was supposed to be. So x-intercept is at 13/4, 0. Beautiful. So that's like roughly 3 1/4, right? Oh, well, it is 3 1/4, but 3 1/4 is roughly there. Very, very, very small. Okay. Let us do our y-intercept now. My favorite. Just plug in 0. Negative 1 over 2 times 0 minus 6 minus 2. That just becomes negative 1 over negative 6 minus 2, which becomes 1/6 minus 2, which becomes 1/6 minus 12/6, which becomes negative 11/6. Am I doing this right? Am I crazy? Okay. You know what? We're going to double check this. Oh, shoot. Am I nuts? Let's double check this, everybody. Let's say as the kids say, what do you think, chat? What do you think? Are you gonna say pog? Let's say, let's do negative 1 over. Say, Mr. Spake knows what pog is. Say yes. Mr. Spake plays video games. 1 over 2x minus 6 plus 2. Now, all I'm verifying here, 3.25. Hey, that looks familiar. And 2.167. Is that 11/6? What? What? Guys, chat, I say. Chat. What happened? +2. You nincompoop. +2. What are you doing? Oh, my gosh. Ugh. Oh, my heavens. 13/6. Oh, my God. What a blunder. A classic blunder. Okay, that works now. It's all good. Alrighty, let's plot that. 13/6 is just a little bit above 2. I'm going to put that there. Yeah? Okie doke, you've got it. So let's put this here. Connect all the way up through this point, and then curving like this, and then the other one like this. Graph it like that. Come on down like so. Okay, and I've just about got it. Let's put our domain in range, and we'll be done with this video. My domain is from -infinity to 3, union, ugly union. Union, oh, terrible union. Union with 3 to infinity. And my range is skipping 2. Sorry that the X and Y intercept gave me some trouble there. I see, no matter how many times you do these things, right, you still encounter those things. Oh, crap, I gotta do general form too. Okay, let's do it. I'll be quick with this. -1 over 2x plus 6 plus 2. Did I get the signs right? -6. You just... It's funny. All right. To get a common denominator here, you need to make the 2 in terms of 2x plus 6. So we're going to add 2 times 2x plus minus 6 over 2x minus 6. And so what this gets me is -1 plus 4x minus 12 over 2x minus 6. The -12 becomes a -13. So 4x minus 13 over 2x minus 6. 4x minus 13, 2x minus 6. And with that, we are done. Yay! Fantastic. I'm going to move this work over. I'm going to move it right over there. Beautiful. Okay. And that is the video. I'm hoping that those 2 examples helped. I hope they were worth the time. I don't know if they really were, but I hope you got something out of it, yeah? Finding these videos either entertaining, useful, or something, even if, whatever. Alrighty. Have a good rest of your day, and I'll see you in the next one.